Well, hello. Let's start lecture three, shall we? We'll continue on what we're doing here. Let me switch to PowerPoint view here. We're going to talk about energy today. And I'm going to go ahead and bring up, well, I guess I can talk to you for a little bit. Then I'll bring up my document camera. So, Chapter two for us in the Changle and Bowles text is kind of this introduction to the first law of thermodynamics. And again, we talked about in lecture one, first law of thermodynamics is conservation of energy. But more than the conservation of energy you probably saw in physics one, where we really just focused on mechanical energy. Here we're going to focus on multiple types of energy. We're going to include what we call the thermal energies, or what I like to refer to as the thermal energies. So you've got heat, and we're going to talk a little about internal energy. We're going to talk about all these as we go along. Heat and internal energy are not the same. Common tendency is to group those two together. They are not. But at any rate, let's talk about energy in general. Energy can take a number of different forms, but the way um, what do we do with energy? What is energy? I'm asking this question here. What is energy? And energy is one of the best definitions I've learned to use for energy is energy is a quantity which influences, move my camera out of the way here, which is going to influence the motion, the temperature, and phase of matter. That's one of the best definitions I've learned for energy. Really like that. It's a quantity that can change how matter is behaving, how material is behaving. And the way it can manifest is it can change the temperature, it can change um, the phase, right? I've got my standard prop here. I've got a bottle of water today. Um, I can I can throw this. I can yeet, as we say these days. I can throw this bottle of water and that I can add energy to it that way, and I can cause its motion to change. I'm holding on to it right now. By holding on to it right now, my hand is putting energy into the water. That's increasing its temperature. The atmosphere around it, I don't know if you can see, there's condensation on that. That means that bottle is cold. Um, so the outside environment is warmer than this water is. I pulled it out of my fridge a little bit ago. Um, so the outside air is adding energy to it, and that's increasing its temperature. If we removed enough energy from this water, it is cold right now. If I continue to remove energy from it, if I threw it in a freezer, I could actually get the molecules to stop moving enough that they'll actually start forming hydrogen bonds with each other, and they'll form a lattice structure we call ice. They'll create a solid. I can add enough energy to this water, right? If I put it on a burner or something like that, or throw it in the microwave, I can add so much energy to it that it'll actually evaporate off into the vapor phase. Right, so I can change the phase, I can change its temperature, I can change its motion. These are all things I can do with energy. How do we measure energy? Energy, as you would have learned in a physics one, is going to be force times a distance. At least that's the definition essentially of one type of energy called work. Work is the application, the net result of applying a force over a distance. We're going to talk about that a little bit today. Um, so any unit of force multiplied by any unit of energy is sufficient to, I'm sorry, any unit of distance. Force times distance gives us energy. The joule, 1 joule is the amount of energy required to, or the amount of energy we would apply if I applied 1 constant Newton over a distance of 1 meter. And of course, we talked last time about breaking these down into their base units. I can break the Newton down into a kilogram meter per second squared times a meter. That is a Newton meter, which is, of course, a kilogram meter squared per second squared. So you can actually break any unit of energy down to mass times distance squared per time squared. The BTU, that is the British thermal unit. It's one of the few English units I'm aware of that has an actual scientific basis. 1 BTU is the amount of energy required to raise the temperature of 1 pound of water 1 degree Fahrenheit or 1 degree Rankine. That is a BTU, a British thermal unit. British thermal unit is about 778 pound force feet. So again, a force times a distance. Foot pounds is often kind of a way of saying that quickly, but pound force feet. That's force times distance. A BTU and a kilojoule are very close to the same amount of energy. They're within about 5% of each other. And so you can see the conversion factor there. And there are all other additional types of energy you can encounter. We don't talk about calories much in this course, but that is an appropriate unit of energy, especially depending on what you're working with. So there are multiple types of ways, multiple units, just like anything else that we could use to measure energy. Now, last time when we introduced the concept of systems, I introduced the idea of a closed system. And I would suggest pause the video here and remind yourself, what is a closed system? Because that's what I would ask if you were in class with me is, what is a closed system? And I would wait until somebody answers me. And sometimes it's a awkward 3-minute pause. So pause here. If you don't know what a closed system is, go look back in your notes from previous lecture. What is a closed system? Okay, we got it. Closed system means there's no mass flow, right? There's no mass flowing into or out of the system. So if we don't have mass flow, there are two ways energy can be transferred to a system. One is heat, which we've mentioned previously. I always like to say heat is brought to us by the letter Q. That is a common variable that we will use to represent heat in most thermal science texts is the letter Q. I think there may be a historical reason for that, and I don't know what it is off the top of my head. But heat will use the letter Q. And then work, which we've learned about in a physics 1. That is the net result of a force applied over a distance, the net energy imparted by a force applied over a distance. Work. If I have, excuse me, if I have mass crossing the boundary, which pause if you didn't look and see what do we call a system where mass crosses the boundary? That has another word. Go look at that up if you don't know. That's control volume. That's right. Excuse me, I'm sorry. If I have a control volume, that means I have mass crossing the boundary either into or out of the system, if not both. And that mass, when that mass crosses the boundary, that mass has its own energy that it brings to the system. So if I have a system where I'm pouring cold mass, cold water, let's say, into a system, that cold water, it still has its own energy. It's still adding energy to the system, but it might be averaging it out to where if I have hot water already there, now I'm bringing in cold water, the two mix together and it kind of averages out. The overall is at a lower energy per unit mass, but the total energy actually ends up increasing. Kind of an interesting way of thinking about it. But at any rate, if mass crosses the boundary, we have to keep track of the energy that mass brings to the system as well. One of my favorite diagrams, this is out of an example out of the Jangle and Bowles text that we're using. We put this fan in what we call a well-insulated and well-sealed room. So well-sealed means it's a closed system. There's no way for mass to cross the boundary. Well-insulated means that I've done everything I can to remove heat transfer between this room and the outside world. So if I have a well-sealed, well-insulated room, and I just put a fan in there, an electric fan, and I turn it on, and the question is, well, what happens? Does the room become warmer or colder? And feel free to pause here and come up with an explanation. Right? So what do you think? Does the room become warmer or colder? Um, well, something to think about here is, what is your system? What are we calling our system here? Because when we do a first law analysis, basically what we're going to do is we're going to draw a system boundary. Right? So what is my system? Well, a system, if you go back and look at your definition, is anything I can isolate from its surroundings is a system. Essentially anything I can draw a dotted line around. So if I draw a dotted line around this room becomes my system now. And then we say, okay, what is crossing the boundary? All right, what crosses the boundary? Well, the only thing coming in is electricity. Electricity is a type of work. We're going to talk more later about why it's a type of work. Apologize, we got a notification there. We'll talk more later about why it's a type of work, but we consider electricity to be a type of work. Um, so I've got energy coming into the system, and that's it. If it's well insulated, there's no heat leaving the room. Um, there's nothing else coming in, there's nothing else going out. I'm just dumping energy into this room. Now, one might look at this and say, well, Steve, we turn on a fan when we're hot? Doesn't that? Yes. But what's happening is when you turn a fan on, now you're blowing air across your skin, and that air it blowing across your skin is going to be at a lower temperature, hopefully, than your skin is. If that air is hotter than your skin, that air is going to basically try to cook you, if you will. It's going to add energy to your skin. But that's why we would turn a fan on in a normal room. Normally, the air around us is cooler than our temperature. So if I blow cooler air over us, that's going to cool us off. But you are adding energy to that air by doing that. You're stirring that air up. And so over a long enough period of time, this is going to increase the temperature of the room. Essentially, you're going to have some heat being emitted off of that fan. And also just simply stirring the air molecules up with the fan blades is going to add energy to those molecules as well. And over a long enough period of time, that represents an increase in temperature. This I love this one, right? Let's put a refrigerator in a room and let's just open it up. The air conditioner's broke, so let's just open the refrigerator up. No, that's not how that works because again, if you've got this well-sealed, well-insulated room, and the only thing, again, first thing we want to do in a first law analysis is determine what is our system and then figure out what is crossing the boundary in terms of energy. Well, the only thing crossing the boundary is electrical energy. That's it. So I've got this room I'm just dumping electrical energy into. And over enough period of time, it's going to increase in temperature. Now, initially, you might get some mixing of that cold air into the room. And so initially, your average temperature in the room might go down. But what if you look, if you take the average between the temperature of the air that was in the refrigerator inside this whole system and now you mix it with the air temperature outside and you take kind of the average before and the average after, you're going to find that it's going to be about the same, honestly. So um, you have to kind of analyze it that way. But again, if we allow this to go after a long enough period of time, if you've ever walked up to a refrigerator that's operating, the coils on the back or underneath, there's hot air coming out of that, right? That's because the way we're going to talk in chapter 6 about how refrigerators work, but it's basically taking the electricity, um, it's taking the electricity coming into the wall and it's removing heat from the food inside and it's putting that energy together, the heat from the food inside and the electricity, it's adding those together and it's kicking that as heat out then into your kitchen or garage or wherever you have your refrigerator. So over enough period of time, this is just going to add heat to the room. Interesting thing to think about though, right? All right. If I add a bunch of energies together, right? If I add a bunch of energies together, I'm going to back up here. We'll talk about that in a second. Um, then I'm just going to use a capital E, right? So a capital E is what's happened when I add a whole bunch of different energies together. Maybe I've got work, maybe I've got heat, maybe I've got kinetic energy, and I throw them all together when I've combined different kinds of energy, because there's multiple kinds we're going to talk about. Then we'll just use a generic E to represent those. Now, that's simple enough, but what I really want us to come away here is this idea of the lowercase variable. The lowercase variable is a very common thing we'll use in thermal sciences to represent what we call an intensive property. We talked about intensive properties not last time or recently. And capital E then is the extensive property. right? It's my 15 minutes here, so I'll wrap up. Um, so you've got intensive properties, which I'll let you go look this up, remind yourself what this means between videos, and then we'll pick up right back here and start the next one. All right, so what is your assignment between here and when you start the next videos? What is the difference between an extensive and intensive property, and why does this make sense? All right, I'm gonna stop here.